This is the final presentation for computer architecture. So today, me and my friend will be going over the Tesla Dojo D1 chip and how it probably will become the most powerful supercomputer in the world for the purpose of training neural networks for artificial intelligence. But otherwise, it also can probably become a very powerful general supercomputer. So we'll go over the chip design and more or less what it does. So before we go into the details of the chip itself, it would be better if we take a look at some general information. And a part of that, I want to talk about Tesla currently. So currently, Tesla is in a situation where it needs a very powerful supercomputer to train AI neural networks, specifically for the self-driving training that it's doing with its Tesla cars right now. So for this kind of training, they require a lot of matrix multiplication and manipulation, because they are gathering a lot of data from video, and that data might be saved as pixels. And to get any type of useful information from that data, they need to do a lot of matrix multiplications. So currently, the general purpose GPUs, which we might put into our computers, are actually pretty good at this type of thing, because they were designed for the purpose of gaming, and we know that the high-end games currently actually use a lot of matrix multiplication for realistic graphics. But the problem is that it's not fast enough for the kind of things that Tesla itself requires, and theoretically there could be a specialized hardware which will do a much better job. And since Tesla announced its Dojo 1 chip, it's no longer that theoretical as we might have thought. So Tesla has 3 different supercomputers right now, which we didn't even know about, and all of them are using NVIDIA GPUs. And as we said, well, because that kind of thing is not a specialized hardware, it's much slower than it needs to be for their purposes. So they are, of course, very powerful, but Tesla and other similar companies which require this kind of specific training for neural networks encounter problems when they want to scale the design of the supercomputer. So the biggest problem that a company might be facing is scaling for either power or for the network. And the bigger problem right now is the information transfer speed, which is basically the network. So in the standard supercomputer approach, we can add more and more modules, but the more modules we add, the slower the transfer speeds will become, because they are limited by the network configuration, which is done in a way that chips cannot communicate really fast directly with each other. So the bigger you make this kind of the bigger you make the supercomputer itself, with the bigger chunks and bigger places, the more networking it will take up, and at some point it actually becomes very inefficient. So it really implies a point where it's no longer it is no longer efficient to scale this kind of process. So it might require too much money, and it might not be as efficient as we might think. So for Tesla itself, it also would be nice that every time they want to expand their design of the supercomputer, that they would not be dependent on another company. So because of all these reasons, they decided to make a chip for themselves. So other general info that I also want to talk about. Currently, we have personal computers which are built in a very specific type of architecture. So there exists a motherboard which we place the GPU separately, and DRAM separately. We have a separate power supply and a GPU, And the CPU itself might also have a built-in GPU in itself. So basically, it's kind of designed for many tasks at once, and it is very good for general purposes and especially for the consumer because we can swap things out. But when we are talking about very specialized problems, it kind of becomes very inefficient. So the problem is that this kind of approach is not as fast as we would like it to be for certain applications. And we need a different kind of computer architecture when we're talking about the kind of things that Tesla wants to do on their supercomputer. So there's another type of design, which is called system on a chip, or SoC for short. So system on a chip is different from the usual type of setup. Unlike the motherboard approach, where we have the motherboard and we can swap the components out, the system on a chip integrates most of the components on a computer on a single microchip. Now, this has a lot of added benefits. And generally, the more tightly integrated the computer system design is, it improves the performance and reduces the power consumption. Of course, power consumption is a very major factor for supercomputers and for scalability, because the more chunks that you place in a single room, the more power you will be consuming, and it also might become very inefficient to run this kind of building. That is actually why most of the companies right now do not build supercomputers for themselves, and they are outsourcing this kind of data training to big companies like Google and Microsoft and Amazon. Well, speed can also be increased because signals can be directly connected to each other with minimal travel time required. It's kind of self-explanatory. If we don't need separate inputs and outputs and pins for the connection to travel from one part to another, it will be faster, and of course the distance also will be lower. So it adds a lot of benefits, but of course it comes at the cost that you're stuck with the chip that you use, and you cannot really swap components out easily like we would on a general computer. So another general thing that I wanted to talk about is wafers. So when processors and chips are manufactured, they are manufactured on a silicon disk, which is called a wafer. So the wafer gets created with a lot of transistors inside it, and it gets cut to become a chip. Now, the thing is that sometimes, and in fact, a lot of times, the chips don't really have full yield. And yield in this case is basically saying that the transistors and the components that are on this silicon wafer chip are not completely operational. So some parts inside it might be damaged, or they might not be working due to the manufacturing process. Now, binning, it is called binning when the manufacturer takes this chip that is not entirely working correctly, and they disable some part of it, and they can either reuse this or sell this chip to the consumer, and by calling it the previous version of the chip. And we have seen NVIDIA, for example, that do this with their processor chips. So they might be manufacturing i9 chip, but because it didn't have a full yield, they might disable the parts which are not functioning correctly, and they might call it i5, for example, and sell it as that by disabling that part and just repackaging it in another way. So, and because of the things that we will talk about, Tesla will not really be able to do this kind of thing, and I'll go into more detail a little later on. So now we can really start talking about the Tesla Dojo D1 chip. So first of all, so Tesla decided to make its own chip with the purpose of creating the most scalable supercomputer possible. So they wanted to add as much cores as they need and have the fastest chip-to-chip communication, so we don't run into the problem of network scalability as we talked about before. And they also want this chip to be designed specifically for the tasks that they want to use it for, and that task would be training artificial intelligence neural networks. So it should be the best chip for that kind of thing, and they want to build a supercomputer which will be completely made out of these chips. So they did quite a bit of research to see the bleeding edge technologies and decided to integrate and improve on them as much as they possibly could. And so it's kind of a thing that we can see that the things that Tesla used in this chip that they tell us about is not really anything new per se, because we see other companies that are working currently on the same kind of technology. But what we see from Tesla is that they have integrated a lot of different things into one single chip, while with other startups and companies, we might see them improving on a very specific single part of the chip. Well, Tesla has the resources to actually do a lot of the improvements at once, which actually creates a very powerful chip. So the resulting chip that we got is the Tesla Dojo D1 chip that we will look at today. So inside of a Tesla chip, there are multiple nodes. And so there are 354 nodes to be exact. And each node has a machine learning module and a CPU optimized around matrix multiplication. So each node also has a large 1.25 megabyte SRAM, unlike DRAM, which is much slower. And as we said, so DRAM is the usual RAM that we might think about. That's the one that we can swap in the motherboard itself. And I have the table in here, which basically compares the different types of memory. So DRAM is on the motherboard, while the SRAM will be on the chip itself or in the core. And we can see the speed difference. If for the DRAM, the speed is 60 nanoseconds. For the cache, it might be 10 nanoseconds. And for the hard drive, it will actually be significantly more than it's written in here. So depending on the kind of cache memory the chip will use, it might be extremely fast for this purpose. So I have found this picture, which is right below the table, which more or less describes how the Dojo chip might work. So we see that in here. So we see the GPU unit, and we see the neural processing units, and we have the CPU units on the right-hand side. And if we zoom into that, we see so 4 different cores, and in here there are outlined 2 cores, and we can speculate that how the cache memory, so there's L1, L2, and L3 cache memory, we can speculate how that would be more or less located on the chip itself. So L2s, L1s, we can more or less see it from the picture in here. So L3 would be shared between different cores, and L2s and L1s would be on the core of each single chip itself. So according to their own statistics, they're able to achieve 1 teraflops of compute. And we'll talk about this kind of statistics and what they mean in more detail later on. And my friend will talk about the specs. So this is another picture that we can see for the node architecture. So as I said, in here it's given the SRAM, and in a little bit more detail we can take a look what is inside it. So we can see the cache memory, the SRAM memory, and other types of things that go into the processor itself in a little more detail. So if we take the Tesla chips, we can see that they are laid out in groups of 25 on a single wafer, basically in a 5x5 layout. And we are actually not exactly sure how a single wafer is created. So there are different theories on how this is done. So the first one is that we might have this. So each 25 of these chips might be separately cut out and then placed on another wafer, or the 25 chips might be or they might not be placed on another wafer, and all of this might be a single wafer itself. So we actually don't know. But so we talked about the manufacturing process of the wafers a little on the previous slides, and we talked about that because for Tesla, we cannot use the process of binning. They need 120 perfectly operational wafers to make the supercomputer work. Now, that's kind of a hard thing to do for a company, but if we compare it to Intel, which in 2014 has made 130,000 chips, wafers of the largest size, with like 60% or something like that success rate. It's definitely not impossible for Tesla to get 120 perfectly operational wafers of these. So no matter how it is constructed, either with 2 wafers or 1 wafer, no matter how it is, it allows for really fast chip-to-chip communication because all of the chips are directly on the wafer itself, and when they want to communicate with each other, they don't really need to use any external wires for that type of communication. So the tiles themselves will be surrounded by high-speed input and output connectors. And because of the way that this training tile is designed, it is very modular, and because of the modularity, it is very scalable. So we can take these units and we can place them next to each other and so on. So it will become a very scalable kind of system. So exactly how modular it is, so we can take the nodes, and if we lay them out on a 2D mesh pattern, we can see that it will become much more efficient and much more powerful. And actually, the efficiency of the computers compared to the loss of bandwidth that you get, it scales linearly, unlike the standard supercomputers that we have right now, which have a downward trend the more processors that you add. So each of these building blocks also act as a high-performance network chip for transferring data with ultra-high bandwidth. And this was one of the interesting parts of the whole chip, that Tesla claims the bandwidth to be 2 times more than the state-of-the-art networking chips that exist today. And that's a kind of a funny metric if you think about it, because this chip wasn't even designed for networking purposes specifically. And it's 2 times faster. So networking training tiles are connected together in a similar way that the PCIe disk, so the fastest kind of memory that we have, drive, would be connected to the motherboard. And the technology is actually exactly the same, but on a normal motherboard, the PCIe would have only 16 ports or 16 signals, and in here so in the Dojo chip, it's not really constrained to 16 signals, which makes it able to transfer a lot of data really fast. So they have a custom kind of PCI connection. So another interesting thing was that the chip actually has a custom instruction set architecture. So it has a custom ISA, as we see from this slide in here. It says that it is a custom ISA optimized for machine learning kernels. So this means that all of the details, how the memory is interfaced with the inputs and outputs and what data types are supported and so on, everything can be controlled by this chip itself. So, and we know that Tesla has already created new data types and custom specialized hardware, which means that they can take this created commands to access this hardware directly, making it very efficient. Okay, so if we talk about scalable communication can be delivered between any 2 chips. So if we take a look at the example in here, we have several chips connected to each other in the layout, the mesh layout in 2D. And let's say that the bottom one and the top one want to communicate with each other. Well, they are diagonally connected. So, and when the nodes want to talk to each other, the other chip can act as a network switch. So it is able to route the data packets through the chip itself. This makes it able to have full bandwidth at each level. So chip to chip, server to server, and rack to rack, which is crazy when you think about it. So theoretically gives you the ability to scale to an arbitrary amount with no networking switches required, because they're already built into the system. And we might, so Tesla's D1 chip might be at the point where the only limiting thing to this arbitrary growth is the software, which would be would have to be optimized to route the data packets correctly to such a huge system. So that might be the only limiting thing, the software, not the hardware now. And so as we can see that so this is a very specialized hardware, which is really not designed for general purpose computing, as we can take a look at the design in here as well. So everything that we have in here doesn't really look like a normal general purpose computer SoC. So even taking out, so it's also speculated that this chip might take out L3 cache entirely, and well, no RAM outside of SRAM, even though there's quite a lot of SRAM. It's very unusual, but as we said, it's very specialized to the kind of thing that Tesla is planning to do. And even though this thing might not really be well suited for general type of computing that we might be interested in, it will work extremely good for the specialized task that Tesla wants to use the supercomputer for. So if we take a look at their own metrics, we can speculate that this will be the 11th fastest general supercomputer in the world, even though it is designed for a very specific task, and it will probably be the best supercomputer in the world for that task, which will be AI neural network training. So the details about the specs and how it compares to other hardware and other information will be talked about by my friend in the second part of this video.
So my colleague has already discussed about the architecture and the speed of Tesla's Dojo, but what does it actually mean, or how can we achieve this speed? Let's dive in. Starting with the performance of the Tesla's Dojo, we saw in the presentation that the single node can achieve 1 petaflop of computing. One chip can achieve 9 petaflops. The cabinet has 100 plus petaflops, and there are 12 tiles of cabinet connected seamlessly through one another. So as a whole, we get 400,000 custom cores of 132 gigabytes of SRAM. As I said, cores are connected seamlessly, and that it means that there is no loss of bandwidth. That is because all the chips act as a part of one big system, as already previously discussed, and that enables it to get more power that reaches to an exaflop, and that is why they call this thing an exapod. So I'm going here saying about flops, exapods, exaflops, but what is a flop? What's a flop? Flops are a floating point of operations per second. It essentially is a scientific notation for a computer to have easier time computing the number. The number of flops means how well can a computer process and do math on a floating points, floats. All this is because there is a limited space to store these floats, depending on the CPU and the system. Generally, it has 1 bit for sign, 8 bits for exponent length, and 23 bits for significant ones, resulting in 32 bits. There is also a type double, that is 64 bits floating number. This way, computer has easier time to express huge and tiny numbers in a limited number of bits. GPUs and supercomputers use flops exactly because they heavily rely on the big calculations on the numbers in order to render graphics, weather absorbing, or machine learning, which is exactly what the main purpose of the Dojo is. As we have already said, Dojo is a supercomputer designed to train neural networks that has almost to no involvement of humans or manual coding.
And our compiler generates code on the fly such that it could be reused for subsequent execution. It has a LLVM backend that generates the binary for the hardware. And this ensures we can create optimized code for the hardware without relying on even single line of handwritten kernel.
Flops have a limited digits as it has a limited space, so it's precise only to the 23 digits in 32 bits and 56 digits to 64 bits. After the dot. At those points they just stop and say, whatever comes next is not important. It's enough. This may seem that floats lack precision and accuracy, especially with supercomputers that need the raw data, but in actuality...
And if you're doing big calculations, it doesn't matter if a tiny, tiny, tiny fraction, something smaller than a molecule, is out, because it'll look more or less right. Right beyond any precision or tolerance that the real world could possibly manage.
As we've discussed what flops are, let's see again how much data can a Tesla exaplot compute. But however, this exaplot value is only in BF16, which is a half precision floating point. For the deep learning, as for the which Dojo is made for, uses FP32, which is a floating point measure for deep learning, and it scales off from previous BF16. With FP32, the Dojo has performance of around 69 petaflops, and in FP64 around 32.38, which puts it into the 11th place. Now you may ask, why are we going so crazy about it? It's only on 11th place. We see other supercomputers perform a lot better and a lot powerful. Even Tesla's GPU cluster 3 itself. So what gives? Why bother about the Dojo at all? And that will be a very good question, my dear viewer. But answer to that is that other supercomputers are built in with flexibility in mind, that they can manage different tasks and run different programs and calculations and programs at the same time without any lags or performance issues. They are built and designed for general purposes. But Tesla's Dojo, on the other hand, is a supercomputer that has a straightforward goal to train neural networks based on 360-degree videos. The entire software and hardware is made to do, first and foremost, this task. The software is optimized to utilize every feature and capability that the hardware can offer. That is why raw computer power does not play that much of a significant role here, and any other supercomputer besides Dojo will run weaker for the tasks that Dojo is made for. Let me make a demonstration on the something more familiar theme. You get the point. One of the major parts of the supercomputer is its size. The size of the tile is small, the person is holding it in his hands. We see that it has gotten rid of all the parts that could have been either unnecessary or redundant. We see how much they've been improving on the technology, ports, and the hardware at once. Unlike our generic all-purpose computers, Dojo is designed with elegance, performance, and compression and modularity. In fact, if all the computers were designed this way, they all would have been way more efficient and smaller. Finally, will other companies and organizations be able to use Dojo and its AI training and tools, or is it Tesla and neural network exclusive? Tesla has significantly automated the AI labeling and training progress so that the machine learning experts can focus on the more difficult tasks. They've also said that their Dojo will be able to be integrated very simply. However, the market for Dojo is quite scarce and it only appeals to those who are either making AI with lots of video simulation and who are using Tesla's labeling and training tools for the AI. So for now, Tesla's Dojo will be of actual use only to them, but as Elon has shown us, what we are skeptical about today may be the safest, fastest, and the most efficient solution for tomorrow. My name is Giorgi Bokhochadze, and this has been my presentation. Thanks for watching. Like, subscribe, and comment on this video. Goodbye.